Hi guys, today what we're going to do is look at drilling steel using a variety of different drill bits or drill tooling, and also using a variety of different drills as well. Now what I have here is a piece of 8 mil thick by 100 mil, which is about 4 inches high by about 3/16 thick in imperial terms. And what I've done is I've marked this out for a number of holes to be drilled here. On the metric side, it's M6, M8, M10, M12, M16, M20, M24, and then we go up to a 64 mil hole saw then at the top. So in imperial terms, we're talking about roughly about a 1/4 inch, 5/16, 3/8, half, 3/8, 25, 32s, 30 seconds even, which is just slightly above 3/4, and then 15/16. So what we're going to look at first is the different types of drill bits that we can use, and there is overlap in between the different types of tooling. Generally speaking, up to about 12 mm or half an inch, especially with handheld stuff, is all done by just straightforward standard drill bits, which are these fellows here. Now there is overlap then from about 12 mm or half an inch up, and what I've done is laid out under each individual hole size to be drilled the different tooling that we can use for those. So M6, M8, M10, so up to about 3/8, or maybe even up to half an inch, we have standard twist drills, high speed twist drills. We also have an annular cutter here in the 12 mil section, and we have what's called a step drill. And a step drill is one of these fellows that cuts just a range of holes in increasing increments as you go up the step drill. So we'll try them all out as we go along. Now, generally speaking, you don't find annular cutters any smaller than 12 mm. The main reason for that is that if we look closely there, we can see that the wall thickness is quite thick and the teeth are quite large, so you wouldn't actually have room in the middle for a hole to cut out a core, and that's what annular cutters do. They cut a core out as opposed to the entire contents of the hole. Now, one advantage that normal twist drills or these fellows will have is that you can drill what's called a blind hole. You don't need to access the rear of the hole to get a core cut out of it, whereas you do with both the annular cutters and the larger hole saws then, which are over here. And the hole saws are effectively the same principle as an annular cutter, but I think what they're made out of is sheet metal, and then the teeth then are sort of a hardened steel or a higher speed steel. Now, when it comes to using or mounting the tooling, the normal twist drills clamp into the chuck on the drill as normal. The step drills do as well. The annular cutters are used in what's called a mag drill, and we'll demonstrate that in a while. And then the hole saws, they use what are called arbors. And there's two different types of arbors. There's this one here for the smaller diameter hole saws. And basically what they do is they just screw on there. And that's effectively it. They just screw on. They're generally reasonably small diameter. Now, when it comes to the larger hole saws, we'll get a different type of arbor, which will have some type of retention mechanism on it to stop the hole saw spinning or possibly over tightening as well. So the way this works is you'll see two keys sitting up here. They retract, and we can mount our hole saw on then, and we just let that go, and the teeth then mate up with the rear of the hole saw itself and stop it spinning on the arbor, and you'll see those holes there. Okay. Now, as an overriding principle when it comes to drilling steel, the big problem is always overheating and cooking out the drill bit. So to remedy that, we've two options or two things that we can bring to bear on that. Number one, we can control our speed, and the second then is we can lubricate and try and cool the drill bit. The annular cutters, which are used in a mag drill, there is a coolant tank on the mag drill, and you can turn that off, and it effectively floods the head or the top of the teeth to keep them cool as you're cutting. Now, with the smaller drill bits and hole saws and stuff like that, what I use here is called sort of a cutting and drilling paste, And effectively what it does is sort of half lubricates or provides some type of lubrication for the very tip of the drill bit as it goes through the steel. And the way that looks like then is just this gloopy stuff here. So that helps cool. Now the more important, or the more complicated bit of keeping the drill bit cool is to do with speed then. Now, when it comes to working out what type of speed we should run our drill at, you could use one of these. This is an engineer's black book, and what this gives us is speeds and feeds for high-speed steel twist drills, and then it gives them to you in a variety of different metals that you'll be drilling: aluminium, copper, steel, and so on and so forth. Now, I copied these out for our different size holes here, and we'll say, as it stands at the moment, a 6mm hole should be running at about 1500 RPM, an 8mm hole about 1200, 10mm hole 950, 12mm hole 796, which is about 800, 16mm hole 597, 20mm hole 477, and then a 24mm hole 382. So you can see the progression there. As the drill bit gets bigger and bigger, or your cutting tool gets bigger and bigger, the RPM of your drill decreases. Now, what I'd suggest there is don't take those particular figures as gospel, because they're published for a particular feed rate through the material and are generally geared for drill presses, bench drills, where you have a lot of rigidity, and you're also able to exert significant downward pressure on the drill bit with the bit mounted in a spindle or a chuck on a sort of a bench machine. When it comes to handheld drilling then, what we need to do then is estimate our speeds. And what we can do is we can look at the side of our drill, and we'll see here that there's a number of different figures given, and this happens to be a 2-speed drill. And again, right, we'll try and get that in. What we can do is, what we will see again is there's 3 different speed ranges here, and that's because this is a 3-speed drill. So you can make a good estimation or get fairly close to where you want to be by setting the gearbox on the drill. If the maximum range of that particular setting is, call it 600, and we want 450, then we're sort of 3/4 of the way on our variable speed trigger. So it'll just give you some approach to getting your speed somewhere right. Now, what I suggest is that, roughly speaking, and this is very much a rule of thumb, or sort of a guess more than anything else, is that if we take those figures that I called out earlier for the machine mounted stuff, we can effectively have those for handheld equipment, and we'd be running roughly about right. Now, when you're handheld drilling, the biggest issue you'll have is trying to exert enough pressure down on the drill bit to actually get the drill bit to bite into the material. So I'd suggest that when you are drilling, drill lower down rather than higher up. If it's over your, mid-chest or thereabouts, you're too high and you won't be able to exert enough downward pressure on the drill. So what we'll do now is I'll set up my piece of steel, we'll mark it out, and we'll mark it out using center punches. And what that does is it creates a dimple in the steel to stop the drill bit wandering when you're trying to get it started off. And what we'll do is we'll drill the first 3 holes with just normal drill bits, and then the 4th hole, which is an M12, we have a number of options available to us, they being a step drill of 12mm, an annular cutter of 12mm, and a normal twist drill of 12mm. So what we'll do is we'll mark our steel for all 3 holes, maybe time it and see how we get on drilling through the steel with the 3 different types. Okay. Now, when it comes to marking out, the first marks you'll make will be with a marker and do your measuring, and then the second will be for the center punch. This is a center punch, and it's used with the hammer. And effectively what happens is you put your center punch where you want the hole, and then, mind your ears, you give it a good thump with the hammer, and what that'll do is leave a dimple where you want the hole to start. So we'll do our first 3 holes like that. Now, that has given us the 3 dimples there for the first 3 holes. And then I'll just go through the second type of center punch, which is this automatic one. And the way this works is that when you press down on it, there's a little cam inside in it which creates pressure, and then when it gets to the bottom, it releases. And I'll just demonstrate that for you now. And generally what I do is I give it 3 or 4 different dimples into it in the same spot, and it makes a deep enough hole. Now that's our piece of steel center punched, so that means then we can start off with our drilling. And I'm just going to rearrange the camera now. We'll clamp the piece of material to the bench, and then we'll start drilling. And what I want to do is set the camera up in such a way that it captures both sides of the steel. Generally speaking, when you're drilling steel, when you're breaking through to the far side, what happens is that the steel sort of blows out a bit, and what can happen there is it can actually jam or catch the drill bit, and either one, trigger the automatic clutch in the drill, or secondly, what happens is that the drill bit will spin in the chuck of the drill, and what you'll get then is sort of a tearing up of the shank of the drill. Now, there's 2 ways of minimizing that. Number one is clamp something to the rear of the material that you're working on, a piece of wood or something soft, maybe a bit of plastic, if you have a bit of plastic board like an old breadboard or something like that. And what that does is it stops it blowing out then, or minimizes it. Or the second option available to us is that as we feel the drill bit starting to break through, is pull it back slightly, increase the speed of the drill, so that what it does, it creates momentum on the drill bit, and then effectively just cuts through that bit that's broken out the far side. I'm not sure whether I'll be able to recreate that now, but we'll see if we can, okay? We'll center our drill bit in the little dimple that we made. Okay, and apologies now, but the camera is between me and the drill. Now what I have is my hand on the very back of the drill, and then the other finger on the trigger. So away we go. Now, as we progress through the back of the hole there, the drill bit didn't catch, but you'll also notice as well that as I'm drilling through, it's very difficult to keep the drill straight. And it's also very difficult to keep a consistent speed on the drill. Now, again, this is slightly more difficult because there's a camera between me and the workpiece, but you get the idea that it's not that straightforward. Okay, on to the next hole. Now, we're set up. We have our 8mm bit mounted in the drill, and I should have done it the last time, but I never put any lubricating fluid on the tip of the drill bit. So we'll stick some of that on there, a little blob in the hole. And away we go. Now, before I start, I didn't mention anything about speed this time. Okay, our speed recommended by the engineer's black book is about 1200 RPM. So I think we'll operate at about 600 mark. And our drill here, again, not 1300 in the middle setting. So what we want is roughly about halfway. Again, this will vary as you're going through the hole. You'll feel it, and your chips should be coming out a sort of a reasonable size. If they're coming out really, really small and like iron filings, you're not pushing your drill hard enough, and you're not eating a proper chip out of it. The chips themselves do provide cooling because the chips are hot and they pull heat out of the hole. So away we go now on our 8mm hole, which is about 5/16. Now we're more or less through to the far side of the hole. So what I'm going to do now is, as I push through, is exert as much pressure down on the drill as I can, well within reason, and I'll also increase the or the speed slightly to push through that last little bit. Now, as you can see, the chips coming out there are looking fairly good. Right, that's, we'll say, a good chip. These aren't bad, but the bigger ones are just pretty much right. So if you're getting a very small chip, you need to push your drill harder into the material. When you're getting chips like the sort of little curly ones there, you're in a good spot there, and your speed and the pressure are just about right. Okay, on to the next hole. Now we're just about to start our 10mm or 3/8 size hole. One thing I forgot to mention previously was that as you progress up to the larger size holes, an intermediate size works well rather than trying to cut a full 10mm or a 12mm hole. So what I have in the drill now is we're back to our 6mm bit, and we'll give it a bit of lubrication this time. And what we'll do is we'll drill a 6mm hole first, and then we'll stick the 10mm bit in and widen the hole with that. Okay, so away we go. Now, as you can see, there's quite a bit of material to come out of the hole. There's a good bit of drilling in it, so take your time. If necessary, even stop for a minute. Let the tip of the drill bit cool down if you don't have coolant, or you can't control the speed. Now, here's a very good example. You might have heard there that the drill bit bound up and is spun in the chuck of the drill. So to get over that, I'm going to reverse it out, and then I'm going to increase the speed and push through. Like that. Now I don't know whether we'll be able to see it underneath, but no, there's no sign of it there, but we'll say sometimes you'll see it, a jagged edge break out. So if that happens, yeah, and you can't clamp something to the back to stop that blowout, pull the drill bit back and go in at a slightly higher speed that the momentum might carry you. Now what we'll do here is we'll have a look at the shank of the drill as well. Sorry, the shank of the drill bit, and see, can we see markings on it from slipping inside in the chuck. And you can see ever so slight scratching there. If that scratching becomes pronounced, sand it down or file it down so your drill bit works in your drill again. It is a sort of an endemic problem with hand tightened chucks. You can only exert so much pressure down, especially when you go to the larger size drill bits. Right, we have a 6mm hole drill there. We'll move our workpiece slightly before we drill into the bench, and we'll enlarge that up to 10mm now. Now, as you can see, there's a bit of smoke starting to come off that drill bit there, so that indicates that I'm running too fast. Sometimes it's not so straightforward to hold a consistent speed when you're drilling, especially with the larger drill bits. But if you see smoke starting to come off, bad sign. So back off and let the drill bit cool. Maybe drill another size intermediate hole if your hole is getting or sorry, if you haven't drilled far enough forward. Let's say if you drill a 4mm hole as a pilot for a 12mm, you're going from 4 to 12 there, which is a decent size circumference of material to remove, and you might want to go up to an 8mm drill bit and do 4, 8 and 12 to get there. Okay, that's our 3 holes drilled with just normal twist drills. So we'll move on now to the next hole, which is a 12mm hole. Now we're set up to start our 12mm hole, and the first process we're going to use is a step drill. And the way these operate is they drill a small hole, then a bigger one, and a bigger one, so on and so forth. Generally speaking, these are used on sheet metal, and they're particularly suitable for that. But I have been asked whether you can use a step drill like this for larger diameter holes in sort of thicker material. Again, this is 8mm material, around 3/16 of an inch, and we'll just give it a go and see how we get on. Okay, so we'll give it a fighting chance now, and we'll lubricate the area. Now, one other issue with step drills is that it's very difficult to control the speed, because theoretically the speed of the small bit at the top here should be way higher than the speed for the wider bit at the back. And we'll say, for example, a 12mm hole, the published figures for that are about 800 RPM, which we're going to have because we're handheld and we can't get through the material as quick as we should. So we'll say this section here should be cutting at about 400 RPM, and this section here, which is 10, 8, 6, about 4mm, should be cutting up around the 2000 RPM mark. So we'll have that and say 1000 RPM. So theoretically, our step drill should be cutting at about 400 RPM on the big bit and about 1000 RPM on the small bit here. So you can see how difficult that would be to manage. So my suggestion there would be start off fast, and then as you progress through the hole and the different cutters are engaging, reduce your speed and see how you get on. So we'll give this a go anyway and see how we travel. Right, we're in our dimple there that we made with our hole punch, and away we go. Now I set this to the first gear ratio, which is 0 to 450, which should be somewhere around right. So off we go. Okay, that isn't making much headway in me there, so what I'm going to do is reverse it out. And I'm going to increase the speed to the middle gearbox range and try and increase the speed until we get down to a sort of a bigger segment of it. Now, as you can see there, it did an okay job. There's fair low pressure when you're pushing through, especially with the larger end of the step drill, but it did an okay job. Now, I did notice some smoke coming off the chips, especially when it got to the bigger end of the step drill, which indicates I was running too fast. So I should have probably stopped, moved the gear on the drill down to the lower range, and just let us sort of chew through it away properly. So that's the step drill, and now we're going to do it with just normal twist drills. And what I'm going to do here is run a 4mm, an 8mm, and then the 12mm to get to where I want to go. Okay, so again we give a blob of cutting paste. As regards our speed, we'd want to be up at around the 2000 mark. So looking at our drill here, the very top speed of the drill is 2000, so that's what we're going to use. So we've already marked out the hole with the punch, and off we go. Now, as we were progressing through that hole there, you could hear the drill bit slip in the chuck of the drill as it tried to break through to the far side. So again, that's the one area that'll destroy a drill bit very, very quickly, is that breakthrough. So try and avoid being harsh there if at all possible. Right, with 4mm done, onto our 8mm intermediate stage. And 8mm should be around the 800 mark. So we'll move into range 2, and about 2/3 of the way will hopefully do us well there. So on we blob, and off we go. Again, reasonably straightforward, and it just shows you the benefits of running an intermediate approach to the hole making. Right, we have our 12mm bit in now, or just about in. We'll give the area a bit of a clean. And again, blob of coolant or cutting paste. Now, our speed here should be around the 400 mark, which tallies up with the first ratio on the drill of the gearbox. So off we go, and we start slow and then off we go. Now, that went through fairly straightforward. Our chips are a good colour. We were starting to get a bit smoky, which means it might be running just a trifle too fast for the size of the drill bit. Okay, on we go then to our mag drill, and we'll set up the mag drill and we'll talk about how that operates. Now, this is a mag drill, which is short for a magnetic drill. And the way these operate is they're effectively a single speed, high powered drill with a switchable magnetic base. Now, the way the magnetic base works is there's a switch on the back, and when you turn that on, it clamps down to the workpiece. Now, the workpiece must be of a sufficient thickness to be or to let the magnetic drill clamp onto it. This one is spec'd at a minimum of 12mm, which is about 3/8 of an inch, but obviously the heavier the material, the more clamping force you have into it. Now, this is fine working on an 8mm plate which will be clamped to the bench. That's reasonably safe. But if you're using this in an upright or an overhead position, you have to make sure that your material is strong enough that you can clamp into it. And secondly as well, these come with a safety chain, and that's especially important if you're working upright or overhead, because a breaker might trip or whatever, and it does happen, and you don't want your drill crashing to the floor via your head or anything like that. So the way these operate then is, I'll just set it up here, is that we have these annular cutters, and what you'll see there is there's two flattened sides to the face, and there's two set screws in the head of the drill, or the chuck of the drill, which clamp onto these two flat faces. Now, there's another little piece of equipment as well, which is called the pilot pin, and that goes through the middle of all the bits. It's a sort of a standardized size, and that provides three different functions. Number one, it allows you to place the center of that pilot directly on the dimple of the hole you made with the center punch. The second function it does, it allows coolant to flow down the center of the bit, or the cutter, and it lets it flood out then onto where the teeth are actually cutting. And the third component, or third function of that pilot bit, is that it provides a sort of a spring to push out the slug of material when you retract the drill fully. So I'm just going to put this in now, and I'll just move the camera slightly to get a better view of the head as I'm putting it in. Now that we're rearranged, what we'll do is we have an Allen key here which operates these set screws in the chuck. So we'll bring this up. I'll give ourselves enough clearance to put the cutter in. we'll take the cutter, we'll stick that in there, and you can see where one set screw is there and the other set screw is there, so that's roughly where your flat faces should be. So that slides in there. Now what I'll do here is I'll let it drop down so that the cutter stays in the drill, like that. I'll stick in my little Allen key or hex wrench, whichever your flavour is. And we'll just snug those up first. And then what we'll do is we'll turn the Allen key around and just give them a good tighten to make sure that they don't slip. Now, I know that all you can see here is the back of my hand, but you'll get the idea anyway. So our next stage then is the drill is plugged in, but neither the magnet nor the motor is on. So what we need to do is align the center of that pilot pin there with the little dimple that we punched out here earlier. So we'll lift this, we'll slide out our drill, and we'll position it over that dimple. Now, I'll just show you that now without my arm in the way. So here's our pilot pin, and it's located just over that little dimple. Okay, so at this stage now, what we do is we turn on the magnet on the back of the drill, and that will clamp the drill to the piece of work. And in this particular instance, because we're working on a steel bench, it'll also clamp the material to the bench. Now I'm going to run this should have coolant running through it and through the drill, but I'll get that all over the lens of the camera. So what I'm going to do is actually run this 12mm bit without coolant, and what we'll do then is when we get up to the larger bits, we'll pull back the camera and just zoom in to try and save the lens of the camera. So I'm just going to operate this now and just show you how it goes. So our magnet is engaged, we'll lift up slightly and we'll turn on the motor on the drill. Okay, so that's the operation of a mag drill, and we don't need to concern ourselves with the speed or the RPM of the mag drill. They're single gear on them, and this one I think is 450 RPM. So effectively what a mag drill is like a sort of a mobile bench drill. It provides its own clamping with the magnet. It's quite powerful. This is a 1400 watt I think, whereas your traditional handheld corded drills would be 800 or 900, and your normal handheld cordless drills would be anywhere between 300-400 watts thereabouts. So it's effectively just a strong slow speed motor with a switchable magnetic base for getting through material, and as you can see it's quite effective at doing that. Now, one last point on a mag drill is that you're not restricted to using those annular cutters with the two flat sides on them. Most mag drills come with a chuck, and this is a Weldon shank chuck, as are all the annular cutters, and all you do then is clamp this in, and then you can put in normal drill bits into this, and I think this is a 13mm or just slightly over ½ inch capacity chuck, so you can run normal drill bits or hole saws or anything that you can clamp inside the normal drill on a mag drill as well, but just bear in mind that your speed is 450 and fixed at that. Now we're set up again with the mag drill. I've coolant this time because we're after moving up to a 16mm hole, and I have the 16mm bit in there, and I've pulled the camera back. So what we'll do now is I'll just demonstrate using an annular cutter. In this case, it's a 16mm annular cutter with coolant this time. The mag drill is clamped onto the workpiece, so we'll turn on the coolant, and as soon as we start to operate, then we should see this coolant start to ooze out there, and it'll cool the the teeth of the cutter for us. Okay, off we go. Now, as you can see, it's a bit of a messy process, but the coolant does work well. And I'll just demonstrate the core that comes out of this. This here now, it's quite hot, is our 16mm core, so it cuts away a lot of it. With the bigger cores, you'll find a much more pronounced version of this. And as you can see, the teeth, we'll pull that back a bit there. The teeth cut away that circumference of material and leave that core in the middle. As you get to the bigger cutters, that core in the middle gets bigger and bigger and bigger, and it's probably why you couldn't find a 12mm the core from the 12mm hole. It was probably just shavings or whatever at that point. Now, while I have the mag drill set up, I'm going to continue on and cut a 20mm hole, which is just over 3/4 of an inch, and then a 24mm hole, which is about 15/16. I won't talk through those, but I want to get those cut because this piece of material is for another video that we'll do shortly. Now, we've cleaned up after finishing off with our mag drill. Now, what we have left here is in the 20mm hole section, which is 25-30 of an inch. We've two other options available to us then. We have the step drill again, and the first time we used that was on a 12mm hole and it worked well. So we're going to run it through now at the 20mm and see how we get on with that. And then we're also going to use a hole saw. Now, this hole saw is 20mm hole saw, and this is the arbor for it, so we'll mount that on the arbor, and obviously that comes with a pilot bit in it as well, and the pilot bits are generally mounted with a set screw. I'll just show you there at the back of it there, there's a set screw there for tightening the pilot bit in it. So that's our two options now. I checked the feeds and speeds here again in my engineer's black book, and what I have here for hole saw cutting speed is in mild steel, 20mm needs about 440 RPM. So just by chance, the lowest speed, or the highest speed in the lowest gearbox, is 450 RPM. So that just suits us fine here for the hole saw. So we'll do the hole saw first, and then we'll do the step drill and see how we get on. But before I move on, I just wanted to show you the slugs that came out of the mag drill in order of size there. That's the one from the 16mm hole, that's the one from the 20, and this is the one from the 24mm hole. And as you can see, it just cuts a slug out, or you know, a core or whatever. I think the 16mm is the smallest one where you'll actually see a core come out of it. No core came out of the 12mm hole. So that's the desired result anyway. Right, away we go with our hole saw. So we'll mount that in the drill. make sure it's good and tight. We're down first gearbox there, number 1. So away we go, and we'll do this one over here. Again, this is punched to stop the drill bit wandering as we drill. Okay. Right, and away we go again. Now, as you can see, it takes quite a while, bit of pressure, and it's difficult to keep straight. So that's our hole saw. So my suggestion would be that once you go above a particular size, that a bench drill would be a better option for a hole saw. Now, our last 20mm option is a 20mm step drill. So we have our step drill in there. Give this a bit of a clean. Now that particular hole saw was actually a 22mm hole saw rather than a direct replacement for the 20mm. I didn't have a spare 20mm one there. Right, we give this bit of lubrication and we'll try it now. Now I'm going to run this at 450 RPM until I get about halfway through the hole. Sorry, I'm going to run this faster at about 1100 RPM until I get about halfway through the hole, and then we'll drop the speed down to about 450 RPM. Okay, here we go. Now we'll drop the speed. Now I'm going to stop it there. I'm about halfway through the hole and I can barely hang on to the drill. So that would tell us then, and I also noticed that the drill isn't exactly straight anymore. So that'll tell us that using step drills is going to be tough. So we got up to about 12mm before it got too hard to hang on to. Okay, so that, as I said, demonstrates step drills. You can only use in a handheld drill up to about 12 or 14mm at most. Okay, now our last hole of the day, we're going to run a bigger hole saw and we're going to try and do it handheld. Again, when you get into the bigger bits, the benefits of either a mag drill or a bench drill for rigidity and the ability to clamp your work down properly is huge. Hand drilling, this stuff, you get away with it once or twice, but if you're doing a lot of it, not advisable. Okay, we'll just set up the big hole saw now and we'll run one big hole just to demonstrate the last of it.